So, welcome to part 2. Where I will focus on metamorphism, sulfides, and ductile deformation. The first part, we, of course, just went over all the different lithologies in Stockholm and the general geological history of the Baltic Shield, Sweden, and Stockholm. Now we're going to go more into the structural and metamorphic history. We'll start, though, first with a little comment on sulfides, because they're very directly linked to the different lithologies that I've just introduced you to. So this is based on my own data set from various different sulfide projects around Stockholm. Wish I could get that to disappear. And you see the number of samples here on the bottom. These are just simple box and whisker plots with also histograms on the side. We call this a violin diagram. And this, on the left side is just the ppm of sulfur, parts per million, and the different rock types that I've already introduced you to. And the main thing to see here is that in the sedimentary gneiss, the metatexite, and the amphibolite, we have higher sulfur contents than what we have in, say, the granite, Stockholm granite, the granitic gneiss, pegmatite, and diatexite. Now, the sedimentary gneiss can be divided into metatexite and diatexite. So the diatexite's those lighter colored melt veins, and this is the darker colored stuff. So it's important to note that these are the metatexitic variant of sedimentary gneiss, and amphibolite are the risk rocks for having higher sulfide contents. And why is having a higher sulfide content a problem? It's because if you oxidize the sulfides in this, then you lower the pH in the groundwater or any water going through it, and that can then leach metals. To explain this kind of diagram a little bit better here, the middle bar here is the median value, the top bar is 75 percentile, the bottom of the box, sorry, is the 25 percentile, and then the whiskers are the 95 and 5 percentiles. Here is a sketch I made myself, which is sort of just an imaginary schematic view of how the sulfides are typically distributed in the sedimentary gneiss. I won't talk so much about the amphibolite because it's not nearly as common in Stockholm as the sedimentary gneiss, and it's distributed in a different way, the sulfides. In fact, it's more commonly pyrrhotite in amphibolite when you have sulfide. Whereas in the sedimentary gneiss, it's pyrite, but when you get down south, it might be more pyrrhotic, depends where you are. But what I've shown here is typical layering. We have more sandy layers, more clay-rich layers, or let's say more quartz feldspar-rich and more biotite-rich layers. And usually the sulfides are distributed in lenses. They're not like, this isn't like pure sulfide, it's just a concentration of more sulfides in these red areas here. And they're more concentrated in the biotite layers usually. And then you can have later structures, brittle structures, or even slightly brittle ductile structures that will remobilize those sulfides and concentrate it even more, that is shown here in yellow. I also try to depict here the fact that these sulfides are spread along the layering, but they also, this LS fabric might also affect how they're distributed in the vertical dimension. It might be stretched out more in the vertical. The main point here is that it's definitely not homogeneously distributed here. So if you're taking this sample here to analyze for how much sulfide you have, especially in sedimentary gneiss, it's very difficult to get a representative sample. So the best way to do it is to knock off a lot of little bits all around the place and combine them into what's called a samlingsprov. If we look again at the distribution of the sulfides over Stockholm based on that same data set, it's not a very beautiful heat map we have of it yet. We need to have better coverage for more tunnels, but we're working on it to get better and better. One thing to notice is that the high concentrations we have here, or these high spots here, Most of them are south of a particular fault here. This east-west boundary, which is around about just south of, around about Hammarby Canal there. But they also trend in a sort of northwest trend. You can't really see it here, but if you zoomed in, you'd see these northwest trends. And one of them, this one here, is right where the diabase dike swarm goes across. So there is probably some sort of association with the diabase dike swarms and sulfides. The sulfides were originally in the sedimentary rock because you were in a reducing environment, the deep sedimentary basin. That's where you can get sulfides forming at the beginning. But the diabase intrusions might have reactivated or remobilized them in some way. We don't know. It's still a mystery yet. But it's important because these, if you have high concentration of sulfides in the rocks and you're blasting them here, making a tunnel or building a house or whatever, if they're too high, they have to go to a repository and it costs a bunch of money to get rid of them, a lot of money, and just classify them. So it's a big problem right now, and we're talking millions to billions of kroner problem it costs. So the more we know about their distribution, and the better in Stockholm. So I had to say about that, and I really want that over there. And I'll just move straight on to metamorphism now. The rocks here in Stockholm are basically generally sit in the upper amphibolite facies. How do we know that? Well, we can see generally the metamorphic assemblages in the sedimentary gneiss and the amphibolite. The fact that we have amphibolite means we're probably an amphibolite and not in green schist facies. Typical metamorphic mineral we see in the sedimentary gneiss is garnet, which you see there, and you can see in the pieces that I passed around. But we also have biotite, obviously, but that's just growing from the clays. And in the amphibole, we have in the amphibolites, we have amphibole. This is often retrograded to biotite when it's especially, and then to chlorite when it's sheared. In the sedimentary gneiss, as I said, we sometimes have garnet, not always. In fact, garnet's more often in the east and southern parts of Stockholm, but in the northern parts, it's harder to find. Why do we not have garnet? It's a good question. It's a little bit of a mystery why we don't. It could be that perhaps these the original sediments here weren't as luminous as normal peelites. They might be greywackies with a primary volcanic source and not the same thing as your typical deep basin mudstones. Or the aluminum's been moved during the during melting into other minerals, and the K feldspar, for instance. We don't know. It's another topic that's worth investigating. One important point, though, is that muscovite is rare, very rare in the sedimentary gneisses here. The biotite, the micas in general, retrograde to chlorite locally where they get sheared. What does this look like on a typical PT diagram? Here are your main key indicator metamorphic minerals. On the left-hand side, we have a metapeelite in a typical PT diagram and how that would develop. And we see here these isograds of melt percent. So we know that we get 20 to 30% melts definitely in Stockholm because we have diatexites. So we know we should theoretically be over here, but we don't, and we assume generally based on the geological history that we're not that deep in the crust. So we should in fact get more cordierite than we often see. We do see cordierite in the south of Stockholm, but it's not so common to or easily to identify an outcrop. But this is the general temperature range, probably even higher, maybe all the way up to here we're at, and maybe the reason why it doesn't follow this diagram perfectly is because this is a general bulk composition of a metapeelite, like I said, that normally would have muscovite in it, which ours don't. So the bulk composition of the Stockholm metasedimentary gneiss might be a bit different than your average peelite. But the main melt reaction that you have that goes on here is you get muscovite plus pelagic clays. Well, if you had muscovite plus pelagic clays to quartz, goes to K feldspar and melt. the same diagram, but for typical basalt, or the predecessor to our amphibolites. Basically, what you get is hornblende and plagioclase go to clinopyroxene and melt when you do melt it here. And you see there's a much smaller amount of melt at the same temperatures than what you would have in a metapelite. It's obvious because the metapelite's got a lot more water in the micas. And water, of course, transmits heat and helps with metamorphism and melting. But you should at least see pyroxene and some melt. And that's what we do see, small amounts in the amphibolite. Now, for the rest of my talk on metamorphism here, I'm going to focus a lot on migmatite terminology because, again, it's the sedimentary gneisses that are the most dominant, and they're interesting. And right now, at the moment, the SGU maps do not differentiate the different migmatitic varieties of this, but they are important because they're, as I showed, the diatexitic versus metatexitic amount of sulfur but also the grain size is totally different. And the amount of biotite is totally different, which is important for what you could use this rock for as a ballast, an aggregate material. Also, it's important for how it deforms brittly when you build tunnels and things. They behave very differently. But in order to do that, you need to understand a bit more migmatitic terminology. So what I'm going to go through first is the first and second order divisions of migmatites. And a lot of these pictures and slides that come up are from the Bible on migmatites, written by Ed Sawyer, Atlas of Migmatites. That's the document down there. The first order division is metatexite and diatexite. That is based on melt fraction. Second order divisions is sort of how the melt's distributed in them, the two different rock types, and that's related to the amount of syntectonic strain, so how much you're stretching or compressing them. So let's go to first metatexite, diatexite melt fraction division. So the model of this is based on two different types of assumptions, either uniform rigid spheres or non-uniform in size and shape spheres. And what are we talking about with spheres? We're talking about the bit of rock that's not melted and not mobile, versus the bit that is mobile. And here you see the amount of melt fraction here on the bottom. So 20%, 40%, 60, and all melt. Here you're in a granite. Basically, you've melted it all and you've got a granite. And what this is showing in the model is how the rock deforms. Is it non-Newtonian or Newtonian deformation? In other words, does everything hold together and you can still have a gneiss when you fold this? And you can see folds that make sense and are systematic. Or has it all become a mush? And that transition in these models typically happens, well, it can depend depending on whether you use these different models types for the remaining rock that's not melted. But generally speaking, that transition happens at around 30% melt fraction. So when you have more than 30% melt, and if you can see more than 30% melt in the rock that you're looking at, then you're most certainly in a diatexite. Now, the differences in the names of in these second order divisions, as I said, are related to how much strain you have during the melting. When you have low strain, the metatexite shows you get a patch or dilatant metatexite. When you have moderate strain, you get net, and high strain, you get stromatic. I'll show pictures of this and go in detail in a minute. The diatexite variety, in no strain, you have what they call a nebulite, looks kind of like a granite. When you have moderate strain, you can get shoulder or raft migmatites, diatexites, and at high strain, you form things called schlieren, which are just like little streamers of biotite, for instance. And I'll show you pictures of all of these. Another really good, and this one's free to download, a book on migmatites is Paulie's book from Western Australia, or South Australia, actually. And here we see, again, the first order division, metatexite versus diatexite. And this describes it better than I just did. The Paleozoic, so the leftover stuff, rock that is not melt, is structurally coherent versus if it's a diatex, it's not coherent anymore. Also, the original Bible in migmatites is Maynard, where he did these beautiful hand-drawn diagrams that you see in the background on the different second order divisions here. Really nice book. And again, I'm going to show you examples of these here. So now we're into the world of metatexite, and we're going from lowest to highest strain. Or I'll go from lowest to highest. Here's the lowest strain. You get a patch migmatite. It's also a lower melt fraction. This is what an amphibolite can look like in Stockholm. You get a little bit more pulling apart. You get maybe some Budens. You get a dilatant metatexite. You pull it out a bit more, and you can start getting melt in these conjugate shears here. That's called a net migmatite, metatexite. And then eventually you deform it enough that you just get these new layers here, and you get a stromatic, so a wavy layered leucosome type of structure here. This one's from Stockholm. So those are the metatexite varieties. Now, if you're mapping for a spatial, for instance, or WSP, or who knows, you're probably going to only make the distinction between diatexite and metatexite. That's already a big advance on mapping in Stockholm. Right now, everybody just calls it gneiss. And if you're lucky, they might say sedimentary or granitic gneiss. So just saying metatexite versus diatexite is a big step. And think, again, 30% melt and some of these other kind of tricks for identifying I'll talk about now. Now I'm going to show a series of pictures of diatexite from Stockholm so you can see it quickly, or try to identify it easily. Here's a picture here from an outcrop. Note the variations in the grain size of these feldspars. You get little, big, medium-sized feldspar. It is not remotely equigranular, not like the Stockholm granite, for instance. It's quite blobby everywhere. You can see everything sort of synmagmatic. It's got a kind of magmatic appearance, but you see these cuspate margins. Here again, we have even more diatexite, even more melt present, and you see these kind of sort of cauliflower-looking feldspars, typical of the diatexite here. Here's the leftover sedimentary gneiss that hasn't melted completely in here. A close-up of that, again, you notice these kind of cauliflower shapes of the feldspar. They don't look like a classic pegmatite like I showed you before. They're always white. Yeah. They're not so beautifully exposed sometimes. Here's a more crappy exposure that you might be more used to seeing. But again, note, strong variation in grain size up to pegmatite size, grain size, so very coarse but strong variation. Very white colored leucocratic rock, almost no biotite in it. Or the biotite in it is in certain layers like shear. In the tunnels, you can see it much more beautifully here, where you can see this sort of this residual, almost aggregate forming diatexite here. You see the little cauliflower blobby texture here. You see the leftover residuum that's biotite rich that didn't melt. Sorry, that melted, but it's just the leftover from the melt. And then you can see the Stockholm granite cutting it right here. Note, we can see that this has been melted quite a lot, but the amphibolite here didn't melt. And we know that, and that's an obvious thing. It's much harder to melt a mafic rock, an amphibolite, than it is a sedimentary rock. And again, the Stockholm granite is later cutting across. Just some of these second order divisions, how they look. Here's an outcrop actually from Canada, if I recall. There you see this nebulitic variety here, where it's, in this case, it's not that there's a lot more deformation, it's just that the melt amount is so big, so much, that it just can't take up deformation anymore. Schollen, which means raft, you can also call it a raft migmatite. Here's the rafts of the stuff that didn't melt inside. And here's the schleric. See this kind of stripy, discontinuous stripy texture to it, usually composed of biotite. Here's a better picture of the schleric. It's almost continuous layering here. But all this stuff in between, all this white stuff is melt. And this is just what's left over residual. Again, you can have Schollen of amphibolite in this particular case that didn't melt. And you have the schleric in between, and then you have these leucosome veins here, the melt veins. Before I show any further that, I'll just show from the camera. Big sample I have of it, because it's a coarse grained rock, you need a big one to understand what it looks like. So here's just a good example of it. And note, here's a little Schollen, or a little Schlieren, probably of biotite in there, a residuum. But you see the different feldspar size. There's a big chunky one. There's tiny ones, there's smaller ones there. There's smaller ones in the matrix. It's incredibly variable and does not have a huge amount of biotite in it. And it is, especially compared to the sedimentary gneiss I showed you before. And yeah, that's what it looks like in hand sample. But you know what? You guys can come up and look at it after. It's going to make quite a bit of noise, I suspect. All right. Now, that's all good and well on an outcrop that I've shown you, or even in the tunnel where you can kind of see it in a larger scale, and you can see around how kind of blobby it is, and you can see those cuspate margins and such. But in drill core, you don't get that kind of context, and it can often look like this. And many people have mapped this as a breccia. And that's not so crazy to think that you have quite angular feldspars here, or bits here. And this can get brecciated at some point in time, but you see how angular this is here with sort of infill. But probably all of this is what we call neosome. So the whole rock has been melted here. It's not all made of melt, but the rock has undergone melting here. That's why it's called a neosome. And we would call this rock a diatexite. There you go. So did I just, yes. Just to introduce a few more terms of migmatitic terms that kind of sit aside from what I was talking about, metatexite versus diatexite, that you might hear people say. You have the protolith. That's the rock that's going to partially melt. That's going to get melted. Anatexis, again, is the word for partial melting. You have the neosome, which is a rock that has partially melted, versus the paleosome, which is a rock that did not melt at all. It's infertile. It can't produce melts. Or it could if you got it hot enough, but it's not in that situation. And then the neosome can be divided up into leucosome, residuum, or melanosome. So these kind of biotite-rich layers I was showing you there. Leucosome is the light-colored melt layers. And then unsegregated neosome, which was a little bit what I've showed there in the tunnel and even in those drill core. The melt hadn't really gotten out of it yet. It was kind of still sitting there with the big blobs of, even what I've shown in the big rock is a bit unsegregated. Now the leucosome, there's 3 different ways to describe the leucosome, but depending on where you are and how, in the scope of it, let's say. So if we take a layer that is a source layer that is easy to melt, has more micas in it, for instance, originally more clay, for instance. We have an in situ leucosome, so these kind of patches and layers that you see that they hasn't moved anywhere. We have an in source leucosome, so that it has moved and it's going along here, spreading in these dramatic ways, but it's still in a source layer. And then we have something called a leucocratic vein or dike. That is coming out of the source layer, but still in the same metamorphic package. And it's the only thing that differentiates these dikes from a magmatic rock is that we're still in our package of similar metamorphic grade. So it's not quite a granite yet, but it's on its way. It gets far enough out of there, it will be, in case you're wondering what those are. How this can look, how this segregation can look during various compression or extensional events. are shown in this picture, and it's kind of what I've already shown you actual pictures of rocks of. But the melt, where does the melt tend to go? Let's say when it's in these packages, it likes to get into necks because you're spreading out. You're making a low pressure area for the melt to come into. Extensional shears like this typical net metatexite, and also you get extensional shears on your between Boudins and Boudin necks, and then also and this is quite common in ore geology to think about when you have hydrothermal fluids, but the same thing happens with melt. You can get it in fold hinges where they open up a little bit and they create space for melts to come in. So just to imagine what this process looks like a little more, I've got this series of events on the left here, and we start with the original package before any melting is occurring, where we have a typical sort of alternating layers of samite, so more sandy rich, peelite, more clay rich, and some calc silicate layers here in blue. So at low amounts of melting at the beginning, let's say, the samite, nothing's happening, these two layers. The peelite, which has more micas, which has more water, which makes it melt easier, starts to form, say, a patch migmatite in this one, and maybe in here we're getting the stromatic migmatite. Maybe this one isn't quite as fertile, and so you can't get them joining together, but we're still deforming things, so we're making stromatic, where this one's more fertile. Nothing's happening to the calc silicates. It's hard to melt a calc silicate rock. And then in the later stage of melting, we're producing more and more melt fractions. The peelites have become diatexites now. The samites are starting to melt, and we have development of scholin, or little rafts here. Here's a raft with a paleosome in it, and we even get schlieren, these little stringers here. And in some of the scholin, we have, as I said, we have paleosome, and the calc silicate layers are getting broken up and boudinaged. That's all I'm going to say about migmatites. So we're going to go now into the ductile deformation in Stockholm. And we start with the earliest ductile deformation that we can see, which is folding. And the fold structures in Stockholm are quite easy to see on just typical LiDAR topography. So this is topography on the left, aeromag on the right. And I think you can all see these larger scale folds. There's a big one here, big one on here in the south. If you look even closer, you can see that fold there. Remember my little sulfide boundary I was talking about, south and north? There's probably there, boundary there. Even smaller scale folds, there's a little one there. On the aeromag, you can see the varmda antiform, much easier here, that's squeezing out here. You can see even smaller scale ones here. So this most easily identified large macro scale folding is caused by north-south compression, probably during the later stages of the Sveckenfinian orogeny, which is the 1.9 to 1.8 GA. So at the same time as these rocks are forming, they're also being deformed and folded. And melting at 1.85 probably is the melting event. That has not been dated. I forgot to mention that. There's all this metamorphism and melting. We still don't know the age of that. It's probably 1.85, but it's not been properly dated in Stockholm. And we know that the melt veins come in often during the folding. So this folding probably is this scale folding is probably at 1.85 GA. I just outlined those major structures here again, here on the Stockholm map. In this SGU report, which is, let's say, the most state-of-the-art description of Stockholm geology besides what you're hearing right now, which is a lot more state-of-the-art and updated since then. There they've named these large-scale structures, the Norrtäljes inform, the Södertörn antiform, and then they have these two tighter varmda folds in between here. It's just basically, I think you can all see it's getting squished there from north to south. Here's, so that's on the very large scale, but the same folds also appear on smaller scales. It's always fractal with folding. And here's what it can look like in sedimentary gneiss. You see that the melt is also folded. In the amphibolite, you can see it's folded here, and here it might be even, this might even be an earlier phase because it kind of looks like it's a xenolith in the melt here, or like a scholin almost, but this isn't diatexite. But still it looks like maybe an earlier event. Here we have granitic gneiss. I'll show this a little bit later. This is in fact a myelinite that's been then later folded. But the folding isn't always just with these subvertical axes, as you saw in the pictures in the map view before, and that's the most common folds you do see in Stockholm have quite steep axes. But here in a tunnel, we see a verging fold here that is in fact almost got a subhorizontal axis. So the folding isn't just as simple as one north-south compression event and steep axes. It's more complicated in its geometry, but we just don't know it. Not much to say about folding there. That was about all we know so far because it's just not known enough in Stockholm. As the deformation continued, this north-south compression during the Svekofeni orogeny continued, and as the rocks into more of a ductile brittle transition regime, we get these these sort of ductile shear zones forming in a conjugate set here. You see the northwestern ones are dextral and the northeastern ones are sinistral during this time period. Here's the squishy foldy bit here showing. And here's some of the major ones you see on a much larger scale outside of Stockholm. But these same types of orientations of shear zones you see, ductile shear zones you see at a smaller scale here in Stockholm as well. So these were active a lot during this north-south compression. But then remember when I pointed out that we have at some point the Trans-Scandinavian igneous belt. So we start getting east-west subduction. And then later on, we get the Sveka Norwegian when North America comes slamming in from the west. And then we even later get the Caledonides slamming in from the west. So after Svekofinian, the most kind of the typical compression events in Scandinavia are east-westerly almost, which have this sort of almost northwesterly to east-westerly, this direction here. And these ductile structures already existed there. These weakness zones already existed, so they get reactivated, but they go in the opposite shear direction because you're pushing from the different direction now. A little trick to always think of to figure out what's the paleo compressional direction here is you can always make an X with these things. So here's an X there, there's an X there, and you see where these bits are pointing in towards. So if you can identify that was a ductile zone, a dextral zone, and that's a sinistral zone, then the arrow will always point into the apex here, where these little arrows point. So here you see that the arrow is pointing where these two, this arrow and that arrow point in. If you made an X out of this arrow and that arrow points there, therefore your major compression is that way. And these faults, of course, develop over time and are being reactivated over time, but the crustal level is also changing the entire time. You're uplifting these rocks and then you're burying them again. So this ductile brittle transition also moves over time. So if we think of a typical weakness zone or a shear zone, way down and deep in the crust, we develop, it's basically just a gneiss, and then you start getting more of like a little ductile shear zone. You start forming, and then you get even more towards the brittle transition. You form myelinites, the shear gets concentrated. You start forming pseudotachyllites, and then breccias and fault breccias and gouges near the surface. But remember, as I said, that might get eroded away. So all you're left is pseudotachyllites and nothing more brittle looking. But then it gets lifted up again, and then you squish it again, and these get reactivated. And so you might have something that has a ductile shear zone that in the core of it has a little fault gouge or pseudotachylite or something else. Here's what these can look like in the real rock. Here we have a ductile shear zone cutting the pegmatite. It's obviously being sheared off here. It happens to go fairly parallel to the foliation around here as well. Here we have a shear zone that's very concentrated now. We're getting into forming almost a myelinite, basically. You see the rock bending in, the foliation bending in here. This would be considered as a parent dextral. And then maybe even in here, if it's probably not reactivated, this one, but if it was, it would probably reactivate along these biotite seams here at a later date. Let's see what these ductile shear zones can look like on a larger scale in Stockholm. If we go here, we look at what's not, this would probably be mapped as a granitic gneiss. We start looking closer at it, we can start seeing that, okay, some of it's not deformed so much. That's probably more amphibolitic and harder to deform. Over here, maybe not so deformed. Here we have a little coarser grain variety of it, and we can see that these feldspars aren't happy. They're quite stretched and oblate. But even within that, so that was probably the older shear zone, ductile shear zone, maybe Svekofinian in age, maybe at the very end of this folding period. And then things get uplifted, or we're at a different structural level, or we reactivate this, and we get a nice myelinite. This is what you'd call a proto-myelinite here, because we can see what the rock was. And then we get this rock, which is an myelinite to ultramyelinite, where everything's been recrystallized dynamically here. And this can happen over and over and over. This is a good example. Here we have a leucosome, so one of these melt leucosomes that has been, it's a lot of people a long time ago would have called this a leptite, which is a metavolcanic, would have thought it was a volcanic rock. But it is in fact leucosome that has been basically ultramyelinitized. And that same leucosome later on gets folded again. That myelinite gets folded again. So we're moving from sort of totally ductile to ultramyelinitic, and then back down to ductile folding again, and then sometimes up again. I think we can maybe take a break again and end this second part of the lecture. And we'll come back for the final bit, which is brittle deformation.